Okay, so Newton had his three laws. He had his universal law of gravitation. He wanted to explain Kepler's laws. That'd be an ultimate test for his description of physics. Now, to do this, if we go back to Kepler's laws, the first one, the orbits are elliptical. The second one, the motion is non-uniform. He has a particular way to describe the non-uniformity of the motion around the sun. And third law is p squared proportional a cubed. Well, to do this, you need calculus. So you're all going, I heard someone actually said yes. I just heard in the front row, which means we don't have to do the calculations here in class. But Newton didn't have calculus. Calculus wasn't invented yet. And so the problem is, think of it this way. Force goes as 1 over the distance squared in the product of the masses. And I put two masses out there. Given this force law, how would they behave? How would one go around the other? How would they orbit each other? Mathematically, how do you figure that out? You need calculus to figure that out. And there wasn't calculus, so he sat down and he invented calculus. There are smart people throughout history. Kepler is pretty clever, realizing that Copernicus's tweak of his model was really an ellipse. It's pretty clever. Copernicus was clever. Galileo was clever. But then there are some people who are just wickedly, scarily smart. And Newton is one of them. Einstein is one of them. I'd put Richard Feynman, who you might not even know. He kind of made his own version of quantum mechanics all by himself that's equivalent to the quantum mechanics that was more standard. I'd say those are the three wickedly smart, scarily smart people in science. There might be others. Newton was one of them. He invented calculus just to solve this and other problems that he had on his mind. Now, at the time, to be fair, someone else invented calculus, Leibniz, around the same time. And you got to be clever to invent calculus, but it puts Newton into a separate class because he invented physics too while he was inventing calculus. Now, Leibniz, he had issue with Newton. Newton's going around saying, I invented calculus, and Leibniz is saying, no, I invented calculus. So he submitted a petition to the Royal Society saying, establish credit here. Who invented calculus? Not very smart, given that Newton chaired the Royal Society and decided in his own favor. So officially, Newton invented calculus. Anyway, okay, so when Newton had calculus in hand, he answered the question. If you have this kind of a force law, product of masses over distance squared, you have two bodies, let's say in the case of the solar system, one is much more massive than the other. What is the path of the other? You work it out with calculus, and it is an ellipse, just as Kepler said, with the central mass at one focus, one of the two foci. Then he said, well, how fast do you travel as you're going around this ellipse? And he worked it out with his laws of physics, laws of motion, using calculus as the tool to actually do the calculation. And he found you go faster when you're close to the central body and slower when you're farther away. It kind of makes sense. The force is stronger. You're going to go faster. And it's exactly as Kepler had described. Kepler didn't have a good way to describe it, so he said you sweep out equal areas and equal times, which is a technically correct description. Newton came up with his description using calculus and then showed mathematically it's equivalent to Kepler's. So he was able to show both Kepler's first and second laws. Then Kepler's third, how does the period, the time it takes to do a full orbit, relate to how far away you are? We know that the planets that are far from the sun take a long time to go around. The ones that are close to the sun, like Mercury, only takes 88 days to go around. We take a year to go around. They're all related by Kepler's third law. He derived that from first principles, and indeed he did. And again, you need calculus to do it in full generality. Now, what we're going to do in class today, so the one person who is excited that we're not going to do the calculation, we're going to do the toughest calculation we'll do all semester today. So now you can say boo. You're not responsive. Don't actually say it. What we're going to do is prove a special case, the case of a circular orbit. Consider a circular orbit, planet going in a circular orbit around the sun. We're going to show that p squared is equal to, or proportional to a cubed in this case, and figure out what that constant proportionality is. Here, let's write it down here. Here's Kepler's third law again, K3. P squared is proportional to a cubed. And we're going to prove Kepler's third law using Newton's laws for the special case of one is a circular orbit, In the other approximation, the mass of the sun is much greater than the mass of the planet. So under those two approximations, we don't need to use calculus, and they're actually pretty valid approximations. The planets are going in elliptical orbits, but they're very close to circular, and the mass of the sun does dominate the mass of the planet, so it's a valid scenario to consider. Now, to prove this, let's write the end result first. Let's write what Newton found. Because you remember with Kepler, he realized that constant proportionality changes with the central object. If it's the sun, it's a certain value. If it's the Earth, it's a different value. Jupiter, it's a different value. And what Newton found, I'll write the whole thing out, using calculus, no approximations yet. This is the constant of proportionality. 4 pi squared divided by g divided by the sum of the masses. Now, for things in the solar system, the second approximation is valid. Big M, which we'll say is the central mass, dominates the little mass. And so m plus little m is approximately just big M. So we can say p squared is approximately 4 pi squared over g capital M a cubed. Things going around the sun. For the moons of Jupiter going around Jupiter. Valid approximation. The moon going around the Earth. Now, our other constraint here is if we're dealing with a circular orbit, the semi-major axis is the same thing as the radius. So this is what we're going to try to prove, that p squared is approximately equal to 4 pi squared over gm r cubed. If we get that far, you can rest assured that if we did a calculus-based proof, we would get a cubed instead of r cubed, and we'd get the sum of the masses instead of the central mass. But we're going to just go for this special case. Y'all ready? Excited? Okay, let's do it. Okay, let's start with a clean page. So here's our central mass. Call that capital M. Here's our little mass. Mass of Earth, let's say. And it's going on, we're assuming a circular orbit. It's close enough to a circle. And it's at a distance r. In constant distance r, because it's a circular orbit. And after a certain amount of time, it's going to move. Let's say in a certain amount of time, t, it sweeps through an angle theta. Now, if there was no force of gravity, the planet would just continue off in a straight line on its last known trajectory, and it would be over here. But there is a force of gravity, and that force of gravity moves it back into a circular orbit, this distance here. Now, before we can put down Newton's second law, or his law of gravity, or any of that, we need to figure out this distance and this distance, given r and theta. So a little bit of setup work's required. This is a skinny triangle, and so we get to use the skinny triangle approximation, but we can write it in full generality. Maybe we'll cheat and just use a little bit of trig just for a second. You don't need it, and then I'll take it away real quick. But for those of you, some of you know trigonometric functions, tangents and sines and cosines. Okay. This is your triangle. This side is r, this is a right angle. This side is r times what trigonometric function? Does anyone know? Tangent, that's right. This side here is r tan theta. Why is that? For those of you who don't know trig, tangent of theta is just the far side divided by the adjacent side. Far side divided by the adjacent side. So r tan theta is r times the far side divided by the adjacent side, which is also r. So r tan theta is the far side. Now, we don't need this to prove it here. If you mess around on a calculator, small angles, tan of theta, if you're in radians, is the same thing as theta. So that's why I went about this. What I'm going to argue here is r tan theta is approximately r theta, where theta is in radians. You can check it on your calculator. Not degrees, put in radians. And what you find is that the small side, the faraway side of this triangle is going to be pretty much r times that angle. And it's true for any skinny triangle. If it's a big triangle, the approximation is not so good. But in astronomy, we're always dealing with very skinny triangles. We're measuring small motions across big distances. If this is r theta, or this is theta, and theta is measured in radians. You can call it the skinny triangle approximation. So we're making use of the skinny triangle approximation there. So that's this side. That's how far Earth moves over this period of time. Whether without gravity or with gravity, I've drawn this with a big angle just so we can see it, but you can imagine a small angle, in which case it doesn't matter. Either the long sides of the triangle are r theta. Let me draw this little triangle bigger here so we can see it more carefully. Oops, this is supposed to go this way. Okay, so we have our mass here. The other mass is up in this direction somewhere. And this opening angle is theta. This distance here is r, and this distance is r theta. We need to figure out this distance now. How far does gravity push it back in this amount of time, t? Well, we can use the skinny triangle relationship again. You need to know this angle, and I'm just going to tell you, some of you can probably derive it from remembering geometry, but we're not going to do that. You can just look at this. This angle here is the same as this angle here. You can prove that with the right triangle. So this angle here is theta, so this angle here is theta, which means this side here is what, if it's a skinny triangle? R theta times theta. Yeah, so r theta squared. Again, this is a skinny triangle, so the short side of the triangle is just theta times the long side, and this is r theta. So it's all nice and symmetric. The distance that we are from the sun is r. In this period of time, we travel r theta, and the force of gravity pulls us back towards the sun, r theta squared. Everyone okay so far? So that was the setup. Now we're going to do the math. Okay, let's pull up Newton's second law. Force is mass times acceleration. I'll ask you to recall for me. Acceleration is defined as change in what over change in what? Change in the speed, or the velocity. So we'll take out acceleration and write delta v over delta t. I guess I'll just call it t. That's why I called it up here. So over this period of time in which the planet moves this far, there's a change in velocity. And velocity is defined as what over what? Yeah? Change in distance over change in time. So this is m delta d over t, whole thing over t. You can write that as m delta d over t squared. Now, we haven't invoked gravity yet. We're not using the law of gravity. This is just Newton's second law. This will be the force that's required to keep the planet on a circular orbit. It's the force that's required to make the planet move this distance over that period of time. Keep it on a circular orbit. So that's our delta D. It's right here. That's the distance over which the force has pushed the planet. So we'll plug that in. We have m r theta squared over t squared. Everyone good so far? Okay, time for a side calculation. Instead of using thetas and t's, let's figure this out here. We've already used this motion here, the force part. Let's use this motion here. How far you would just travel over this period of time. For that, we can pull out our old friend. Distance is speed times time. So over this period of time, we travel what distance? R theta. R theta is equal to v times t. Let's solve for t. And we're going to plug that in here. So divide both sides by v to get t by itself. So the period of time for us to move through angle theta is r theta over v. Plug it in here. M r theta squared divided by r theta over v squared. It's going to be m r theta squared divided by r squared theta squared over v squared. The theta squares cancel. One factor of the r cancels, and the v squared will be flipped up to the numerator, giving you mv squared over r. And this is a very famous foundational equation in physics, derived in this way. The force required to keep you moving in a circle is equal to your mass times the speed squared divided by the radius of the circle. We haven't used gravity yet. That's coming up immediately. But this is the force that's required to keep you in a circle. Now all we have to do is set it equal to Newton's force of gravity. Everyone with me so far? Okay, good. Give you a chance to write that down. I'm going to flip pages. 3, 2, 1. Okay. So what we just derived, the force required to stay in a circle is mv squared over r. And we're going to just set this equal to the force of gravity, because that's the force that's pulling you in a circle. That's gmm over r squared. That's the force of gravity from Newton. Now let's see here. The m's cancel. One factor of the r cancels. So we have v squared is gm over r. And we'll take a square root of both sides. So we get v is equal to the square root of gm over r. And I'm going to put a subscript c, because we're considering circular orbits, and this is another important equation. If you're traveling in a circular orbit, the speed at which you're traveling depends on the mass of the central object and your distance from the central object. This is defining the characteristics of the orbit, motion under the force of gravity. Interesting aside, it doesn't depend on your mass. How you move in a gravitational field does not depend on your mass. It depends upon the mass of the central object. Let me demonstrate that. I wasn't planning on doing that, but it's an easy thing to demonstrate. Here's a piece of chalk. It's low mass. I don't know. Let me find something heavy. That'll probably break. Oh, okay. Yeah. Oh, this is plastic. If it breaks. Let's go for the heavy one, even if it breaks. This will teach you to leave your stuff in the room. Okay. Yeah, that's the lost and found, by the way. It's getting bigger. So a piece of chalk in Earth's gravitational field weighs, hardly any mass. And this canister here, water in it, so it's heavy. It has mass, a lot of mass. Same gravitational field. You've seen this before. They're both going to hit the ground together, hopefully. Here we go. It didn't break. So if that's your canister, you can come up and collect it still. But just a demonstration that it doesn't depend on your mass. It can't. Well, it sort of didn't break. It's a little dented. Okay. Here's my pen. Just an aside. The motion depends upon the central mass. Another way to think about this, if we got rid of the Earth and replaced it with a speck of dust, traveling in the same direction at the same speed, it would continue to travel the same orbit. It doesn't depend upon the mass. Now, if you go at a different speed, you won't have a circular orbit. So here's a slide showing the space shuttle. And if you go at just the right speed, you will get this circular orbit. Where is my cursor? Here. Going around the Earth, just like Newton's cannon. If you fire with a lesser speed, you'll be on an elliptical orbit, and you'll, of course, intersect the ground. So we call that a suborbital flight. You kind of go up and come back down. If you are moving with greater than v sub c, you go into a big elliptical orbit. You come all the way back around to your launch point. But if you go with even more velocity, you hit the escape speed. And I'm just going to write this down. The escape speed is not that much faster. We'll use this equation later in the course. We won't derive it, but it's so similar to the circular speed, I'll just write it right here. Just an extra factor of 2 under the square root. Square root of 2 is 1.4. So if I send the space shuttle going 40% faster than I should have, it's not coming back. So you got to be really careful when you put rockets into space. An error of 40% means the difference between it coming back and not coming back. I mean, that's why they call it rocket science. It's precision work. Anyway, that was an aside. Let's wrap up this proof. So to wrap it up, we're going to consider the full orbit. And we're going to again use distance as speed times time over the course of the whole orbit. So in one full orbit, the distance you travel is what? The circumference, which is given by what? 2 pi r, yep. 2 pi r. The speed that you travel is the circular speed, so square root of gm over r. That comes from Newton's force of gravity, equated to his second law of force to keep it in a circular orbit. And the amount of time to do a full orbit, we call that p. Square both sides, we have 4 pi squared r squared is equal to gm over r p squared. Now let's get p squared by itself. We'll multiply both sides by r over gm. R over gm. So the gm's cancel, the r's cancel, and we get p squared on this side. On this side we get 4 pi squared over gm and 3 factors of r, so r cubed. And that's our equation. It's written backwards, but p squared is equal to some constant times r cubed. That's Kepler's third law. Right here, p squared is 4 pi squared over gm times r cubed. So you've been proven that you can derive Kepler's third law from Newton's laws, at least under this special case. Happy? Oh, yeah, you like that. Wow. Now let me fire up this little thing here. Let me just mention again the other cases. So let's consider, we made the simplifying assumption that one mass dominates. But there are many systems out there, like binary stars, where the masses are similar or pretty close to equal. What happens in this case is one doesn't orbit the other and the other doesn't orbit the one. They both orbit a common point called the center of mass. And if you work out the full description, you'll get this kind of behavior, and you'll get the m plus m in the denominator, which we didn't have in our derivation. Here's a real-world example. Sirius, the brightest star in the sky, it's actually a binary. Sirius A is more massive than Sirius B. So you can see the center of mass. The more massive one still moves, but it's a smaller circle. The less massive one is now moving in a bigger circle, or ellipse, actually.
They just share a common foci? Or how that works, essentially?
Yeah. You can rewrite the equations in terms of its motion around the center. The center of mass is actually at the focus. And then again, here's the case of our solar system where the mass is concentrated at the center. After the sun, most of the mass is in Jupiter. So you can think of it as a binary Sun-Jupiter system. There's indeed a center of mass. It's about 1 solar radius from the center of the sun. So the sun doesn't just sit there. It does move around its center of mass. If this is the sun, the center of mass is kind of right here on its outskirts. And so as Jupiter's over there, it kind of wobbles around this point like that. But it too is behaving by the full equation here.